Imagine you have a coin sitting flat on the table. That coin is either heads or tails, one or the other. There is no in between. Now imagine spinning that coin. While it's spinning, it's kind of both heads and tails at the same time. You don't know which it is until it falls and you look at it. That spinning coin, believe it or not, is one of the best everyday analogies we have for understanding the fundamental idea behind quantum computing. And today we are going to unpack exactly what a quantum computer is, why it matters, and why some of the smartest scientists and engineers on the planet are dedicating their entire careers to building one. Let's start with what you already know. The computer you're using right now, whether it's a laptop, a phone, or a desktop, is a classical computer. Everything it does, every calculation, every video it plays, every message it sends, is built on something called a bit. A bit is the most basic unit of information in classical computing, and it can only ever be one of two things, a 0 or a 1, off or on, false or true. Every single thing your computer does is a massive, extraordinarily fast sequence of zeros and ones being shuffled around and processed. Your computer is incredibly good at this. Modern classical computers can perform billions of these operations every single second. And yet, there are certain problems in the world that are so complex, so mind-bendingly large, that even the fastest classical supercomputer on Earth would take longer than the age of the universe to solve them. This is where quantum computing enters the picture. A quantum computer doesn't use bits in the classical sense. Instead, it uses something called a qubit, short for quantum bit. And a qubit is fundamentally different from a classical bit because of a property in quantum mechanics called superposition. Superposition is that spinning coin we talked about. A qubit doesn't have to be just a 0 or just a 1. It can exist in a combination of both 0 and 1 at the same time, right up until the moment you measure it. This might sound like a small difference, but the implications are staggering. If you have two classical bits, they can represent one of four possible combinations at any given time: 00, 01, 10, or 11. But two qubits in superposition can represent all four of those combinations simultaneously. Add more qubits and the number of simultaneous states grows exponentially. 30 qubits can represent over 1 billion states at the same time. 300 qubits can represent more states simultaneously than there are atoms in the observable universe. This is what gives quantum computers their theoretical power. But superposition is only part of the story. Quantum computers also exploit two other deeply strange properties of quantum mechanics. The first is entanglement. When two qubits become entangled, the state of one qubit is instantly connected to the state of the other, no matter how far apart they are physically. Change one, and the other responds in a correlated way. Albert Einstein famously called this spooky action at a distance, because it troubled him deeply, yet experiments have proven it to be absolutely real. In a quantum computer, entanglement allows qubits to work together in a coordinated way that has no equivalent in classical computing. The second property is interference. Quantum algorithms are carefully designed to use interference, the same phenomenon that causes waves to amplify or cancel each other out, to amplify the probability of reaching the correct answer and suppress the probability of reaching wrong answers. Together, superposition, entanglement, and interference are the three pillars that make quantum computing a fundamentally different kind of computation. Now you might be wondering, if quantum computers are so powerful, why isn't everyone using one? The answer is that building a quantum computer is one of the hardest engineering challenges humanity has ever attempted. Qubits are extraordinarily fragile. They need to be isolated from virtually every form of external interference, vibrations, heat, electromagnetic noise, because any disturbance from the outside world causes something called decoherence, which essentially means the quantum state collapses and the qubit loses its special quantum properties. To prevent this, most quantum computers today need to operate at temperatures colder than outer space. We're talking about temperatures close to absolute zero, which is around negative 273 degrees Celsius. The engineering required to maintain those conditions is enormously complex and expensive. On top of that, qubits are prone to errors, and quantum error correction, the science of fixing those errors, is still an area of intense ongoing research. So where do things stand today? As of right now, we are in what scientists call the noisy intermediate scale quantum, or NISQ era. The quantum computers that exist today, built by companies like IBM, Google, and IonQ, have dozens to a few hundred qubits, but they are noisy and error-prone. They are impressive achievements, but they are not yet capable of solving practical real-world problems better than a classical computer in most cases. That milestone, called quantum advantage or quantum supremacy, has been demonstrated in a handful of very narrow, carefully constructed experiments. But a fully fault-tolerant, general-purpose quantum computer remains a future goal. Most experts believe we are still years, possibly decades, away from that. But that future is worth working toward because the potential applications are breathtaking. Quantum computers could simulate the behavior of molecules and chemical reactions at a level of detail that is completely impossible for classical computers, potentially accelerating the discovery of new medicines and materials. They could transform the field of cryptography, breaking many of the encryption systems that protect your data today, while also enabling entirely new and theoretically unbreakable forms of encryption. They could optimize complex logistics systems, improve artificial intelligence, and help us model climate systems with unprecedented accuracy. Quantum computing is not a replacement for your laptop. It will not make your videos load faster or make your video games look better. It is a completely different kind of tool designed for a completely different class of problems. Problems of such staggering complexity that they sit beyond the reach of any machine built on the physics of the everyday world. It is a tool built from the strange, counterintuitive rules of the quantum world. A world where particles can be in two places at once, where measurement changes reality, and where two particles can share a connection across any distance. It is, without question, one of the most fascinating frontiers in all of science, and we are just getting started.